I'm representing the structural chemistry program at the Department of Chemistry, Edström, and I am Kristina Edström. And we work on structures in motion. Atomic structures and methods for determining atomic structures is one of our core methodologies. But just to see a solid material as a solid and not realizing that there can be ions moving in these structures that can be used for different things has become one of our main activities, something we really are interested in, because to describe the mechanism for how the solids will respond to these mobile ions is not trivial. So we use experimental techniques, we use theoretical techniques for this in our program. And I have put up as an example some of our core activities in this program, which is to study batteries. Batteries and fuel cells, useful for instance, the car industry, or for you when you have your mobile phone or your laptop. I think you all agree that the batteries could be better and charge more seldom than they are done today. And we are focusing on the chemistries of lithium and sodium-based batteries. And this is just one example where you see an example of an atomic structure of an iron-based compound as the positive electrode and graphite as the negative electrode. And this is today a commercial battery. And what's happening when you are using your battery is that you have lithium ions in the positive electrodes, and you have to charge your battery to put them into between the sheets of a graphite. And this is not just putting the ions into between the layers, but because the layers will respond to this motion. And then you can use your battery. And the fun thing with these batteries is that there are so many different materials. So you can actually play with the chemistry of the negative electrode, the chemistry of the positive electrode, and optimize your battery for the application where it is to be used. And to doing that, you need to understand how to synthesize materials, how to study the crystallinity of a material. The more crystalline this material will be, the more efficient it will be in handling this transport of ions. And the lithium ion, as you know, is the smallest ion of all in the periodic table. And it also gives this battery a potential difference of almost 4 volts. That's why it's so powerful. So it's the most powerful of the rechargeable batteries we have today. It's just one issue. Lithium you find in Afghanistan, you find it in Russia, in China, in South America. So even though there is a lot of lithium to really upscale this battery for electric vehicles, which is actually the issue today, and even for large-scale storage in the grid, it's a geopolitical issue that you don't find the lithium everywhere. So therefore, the second alkaline metal in the periodic table, sodium, is one important possibility. Now, it's not only the positive and negative materials you have to have in a battery, you have to think about the electrolyte and the transport of lithium ions through this electrolyte. And there you also have the transport, the mobility of ions as an issue. And this can be a liquid, it can be a solid, a polymer electrolyte. And in our group, we actually work a lot with the different chemistry programs here at the Edström lab. So we have a big program with polymer and Tim Bowden, where we actually look at the new electrolytes that can be used to really make these efficient batteries. And when you talk about 14% efficiency for solar cell, I talk about 95% efficiency when it comes to battery of this kind, and that's why it's so interesting. And you can cycle this for many thousands of cycles repeatedly before you have a lifetime that decreases, which is much better when you can do it with the lead-acid battery. So, and it's not only that you need new positive, negative, and electrolyte materials. You have also to think about the interfaces. And characterization techniques to understand what's happening here. So, the structural chemistry group is a big program. We're about 70 people. We're constantly looking for new PhD students. And we have 2 main professors, and we are 2 strong females. So here you have woman power. So I am more responsible for the battery part, and Kersti Hermansson is responsible for the theoretical inorganic chemistry. Also looking at dynamic processes in materials. She is very interested in catalytic processes and in ions in solution, which is exactly what we might have in the battery. So that's interesting. And this is just one example of our achievements. A completely new iron-based positive electrode material, but that can work at 60 degrees rather efficiently, and which opened up a whole research field in the world, where many groups now are working in something we started. And for those of you who looked at the news on Sunday evening, you saw an example of actually not only inorganic materials, but that we also look at organic materials as positive and negative electrode materials. The director of study, Daniel Brandell, have you met him? No, never. No. He then presented how you can use pine tree and get organic molecules from that can work in a battery. So there are many different things that boiling around, but everything comes back to structures. And you can think about structures not only as flat, 2-dimensional structures, you think them as 3D structures. A lot of surface area on a small footprint area, and also not only make big batteries for vehicles, but also make miniaturized batteries to really make efficient batteries. And this is just one example of what you can do. You make your electrode rather flexible, and you can make it of nanotubes, where you grow iron oxide sticking out from this nanotube. And you can make very interesting structures and testing batteries with rather good cycling. This is supposed to be a cycle number and how good sort of capacity you can get out of it. And I just wanted to show you how the theoretical inorganic chemistry with Kersti and Peter Brookquist, what they do. They look at chemistry of metal oxides, and there's a lot of these kind of catalytic reactions to model how a surface looks and how an atom can react on this surface, what the defects in this surface will mean for the heterogeneous catalysis. They also look at metal ions in solutions and how these solution molecules can coordinate around this metal ion, and look at hydrogen bonds and vibration spectra. They not only look at these systems, they also try to develop their theoretical methods to come to an even stronger understanding from a theoretical point of view by looking at really detailed atomic level, going up to more and more systems in their approach. And this is one molecular dynamic simulation of a nanoparticle in a solution. And here you can see the water molecules and their hydrogen bonds around this nanoparticle and how you have this dynamic process. So I'd like to end here by saying that dynamic processes are really interesting to study. They can be very useful for our daily life, and it's really a lot of fun to work with complex systems that can mean something for us and our society. So thank you very much.